6 mysterious ancient artifacts that stunned even top scientists. Let me ask you something before we begin. How certain are we that the story of human history is complete? That everything important has already been found, dated, and neatly explained? Or is it possible that some discoveries do not belong where we have placed them? Welcome to the Silent Vault channel, where we explore the mysterious, the incredible, and the archaeological discoveries that make even scientists pause in awe. Today, we're opening a quiet door into the past to examine 6 artifacts that unsettled even the people trained to explain them. These objects were not just old, they were unexpected. They hinted at technologies, methods of communication, advanced craftsmanship, structures, and even maps that seem far too precise for the eras they came from. If you enjoy exploring unanswered questions and forgotten evidence, don't forget to like, subscribe, and turn on the notification bell so you don't miss what comes next. Now, let's begin this journey with our very first discovery: the Baghdad Battery. In 1936, a German archaeologist named Wilhelm Koenig was cataloging artifacts at the National Museum of Iraq when he noticed something unusual among the Parthian-era finds. Clay jars, roughly 5 inches tall, each containing a copper cylinder. Inside that cylinder sat an iron rod, corroded but intact. The cylinders were sealed at the bottom with asphalt. The construction was deliberate, careful, specific. Koenig wasn't looking for evidence of ancient electricity, he was documenting pottery. But the design of these jars kept pulling his attention back. The copper cylinder didn't touch the iron rod. The insulation at the base prevented contact between the metals. It looked, to him, like the internal structure of a galvanic cell, what we would call a battery. He published his theory in 1940, suggesting these jars from ancient Mesopotamia, dating to somewhere between 250 BCE and 250 CE, might have been capable of generating electric current. The idea was met with skepticism, as it should have been. Extraordinary claims need substantial evidence, and Koenig's interpretation relied on functional possibility rather than historical proof. But the question he raised didn't disappear. The Parthian Empire controlled much of what is now Iraq and Iran during the period these jars were made. It was a civilization known for skilled metalwork, elaborate irrigation systems, and trade networks that connected the Mediterranean to Central Asia. They produced intricate jewelry, worked with diverse alloys, and demonstrated a sophisticated understanding of materials. Could they have also understood, in some practical sense, how to generate electrical current? Researchers who wanted to test Koenig's hypothesis built replicas. They filled the clay jars with an acidic solution, vinegar or citrus juice, substances available in the ancient world, and inserted copper cylinders and iron rods in the same configuration. The result was measurable electric current, typically around 1 volt, enough to produce a mild shock, enough potentially to drive a chemical process. This is where the mystery deepens, because generating current is one thing, having a reason to generate it is another. If these jars were batteries, what were they used for? One theory involves electroplating, the process of depositing a thin layer of metal onto another surface using electrical current. Several artifacts from the same period show evidence of gold or silver gilding that appears unusually even and adherent. Modern electroplating relies on this exact principle. Immerse an object in a solution containing metal ions, apply current, and the metal bonds to the surface. Could ancient craftsmen have discovered this process through trial and error without understanding the underlying physics? It's plausible. The chemical principles aren't complex. A copper vessel, an acidic solution, and the right configuration of metals would produce the effect. Whether they thought of it as electricity is irrelevant. They would have observed that this setup made gilding more effective. Another possibility is medical. Ancient texts from various cultures describe treatments involving electric fish, rays, and eels that produce natural shocks. Physicians used these creatures to treat pain, particularly headaches and joint ailments. The shock therapy was real, documented, and apparently effective in some cases. If Parthian doctors had access to these jars, and if they understood that filling them with certain liquids produced a tingling sensation when touched, they might have used them as a controlled alternative to handling live electric fish. But here's the complication. We have no written records describing their use, no instruction manual, no medical text mentioning clay jars and treatment protocols, no artist's depiction of electroplating workshops. The jars were found in archaeological contexts alongside other household and workshop items, with no special ceremonial placement or protective storage. They were common enough that several examples survived, but not so common that we find them everywhere. Some archaeologists argue they weren't batteries at all. The design, they suggest, could have stored sacred scrolls. The asphalt seal would protect parchment from moisture. The copper cylinder would provide structural support. The iron rod might have been added later or might have served as a mounting point. It's a simpler explanation, one that doesn't require us to reimagine the technological landscape of the ancient world. Others point out that the copper cylinders show corrosion patterns consistent with exposure to acidic substances, patterns you wouldn't expect if they only held dry scrolls. The debate hasn't been settled, partly because many of the original jars were lost or destroyed during the looting of the National Museum of Iraq in 2003. Photographs and descriptions remain, but the physical evidence has become scarcer. What stuns scientists about the Baghdad battery isn't necessarily proof of ancient electrical engineering. It's the reminder that technological knowledge doesn't always follow a straight line. Discoveries get made, methods get used, and then they vanish from the historical record when circumstances change, when empires fall, when trade routes shift, when the people who knew how to build these things die without passing on their knowledge. The Baghdad battery sits in that uncomfortable space where the evidence suggests capability without confirming intent. We know these objects could produce current. We don't know if anyone meant them to. And that uncertainty, more than any definitive answer, captures something essential about archaeology. The past is full of things that worked without leaving behind an explanation of why. The Roman dodecahedra. Picture a bronze object, small enough to fit in your palm, 12-sided, hollow, with circular holes of different sizes punched through each face. Small knobs protrude from each of the 12 corners. The craftsmanship is careful. These weren't crude castings, but finished pieces, often decorated with circles or dots around each opening. They've been found across Western Europe, from Britain to Hungary, in regions that were once part of the Roman Empire. More than 100 have been discovered, and no one can agree on what they were for. These are the Roman dodecahedra, and they represent one of archaeology's most persistent puzzles. Unlike most artifacts, which come with contextual clues, found in temples, they're religious. Found in kitchens, they're domestic. Found in workshops, they're tools. Dodecahedra show up almost randomly. They've been unearthed in military forts, civilian settlements, rural fields, and river deposits. No contemporary Roman text mentions them. No inscription explains their purpose. No artistic depiction shows one in use. The earliest known example was found in the 18th century, and archaeologists have been proposing theories ever since. Every proposed function has something going for it and something that doesn't quite fit. One popular theory suggests they were surveying instruments, devices used to measure distance or determine the optimal planting dates for crops. The different sized holes could function as sighting tools. Hold the dodecahedron at arm's length, look through one hole while aligning a second hole with the horizon or a distant object, and you might be able to calculate angles or distances. Some researchers have tested this, and it works, to a degree. The varying hole sizes would allow for different measurements depending on which faces you used. But if they were surveying tools, why are they so ornate? Roman engineers had simpler, more efficient instruments for measuring angles and distances. The groma for laying out right angles, the chorobades for checking levels. These were standardized, practical, documented tools. Dodecahedra, by contrast, vary in size and exact configuration. Each one is slightly different, which would make standardized measurement difficult. Another theory posits they were candlesticks or lamp holders. The hollow interior could accommodate a light source, and the holes would allow light to project outward in patterns. The knobs at each corner could prevent the bronze from getting too hot to handle, or they might have served as feet to keep the base stable. It's not implausible. Romans used a variety of lighting devices, and a geometric bronze lantern wouldn't be out of place in a wealthy household. Yet many dodecahedra show no evidence of soot or heat damage inside. If they held candles or oil lamps with any regularity, you'd expect carbon deposits, discoloration, or warping. Most examples are clean inside, the bronze patine consistent throughout. A more elaborate suggestion comes from textile historians who believe dodecahedra might have been used in glove making or knitting. The holes could guide different thicknesses of yarn or leather cord. The knobs might anchor the material while working. Eye coordinating, a technique that produces narrow tubes of fabric, could theoretically be done using a dodecahedron's holes to control tension and diameter. Experimental archaeologists have attempted this, and it's possible, though awkward. Whether it's more efficient than simpler tools is questionable. Then there are the ritualistic interpretations. Perhaps these objects held symbolic meaning, 12-sided to represent the zodiac or the months of the year, the varying holes corresponding to different celestial or agricultural cycles. They might have been used in ceremonies we no longer understand, their function more about representation than practical utility. This would explain why they weren't depicted in everyday art or described in technical manuals. Religious objects don't always get documented the same way as tools. But Romans were generally forthcoming about their religious practices. We have extensive records of rituals, priesthoods, sacred objects, and ceremonial protocols. If dodecahedra held religious significance, it seems odd that not a single text or inscription would reference them. What makes the dodecahedra particularly frustrating is their widespread distribution and consistent form. This wasn't a local oddity or a one-off experiment. These objects were made across multiple provinces over several centuries with enough regularity that the basic design remained recognizable. That pattern suggests a shared understanding of purpose, something people across the empire knew these objects were for, even if the knowledge didn't survive in written form. Material analysis offers a few more clues. Most are made from bronze, an alloy of copper and tin that was valuable but not extravagantly so in the Roman world. The casting technique shows skill. Creating a hollow 12-sided object with precise holes and symmetrical knobs required competent metalworking. They weren't mass-produced in the way that common pottery was, but they also weren't rare luxury items restricted to elite contexts. They occupied a middle ground, well-made, distributed widely, common enough that we keep finding them, but not so common that everyone had one. Some scholars have suggested they were simply curiosities, geometric toys or decorative objects with no practical function at all. Romans appreciated craftsmanship for its own sake. A beautifully made bronze dodecahedron could have been a display of skill, a conversation piece, or a mathematical demonstration. This would explain the care and construction without requiring a utilitarian purpose. But even this explanation feels incomplete. Toys and decorative objects usually appear in specific contexts, in homes, in graves, in markets. Dodecahedra show up in such varied settings that a purely ornamental function seems unlikely. Tools have context, religious objects have context, even toys have context. These have almost none. What stuns scientists about Roman dodecahedra is the combination of ubiquity and silence. Here's an object that clearly mattered to people across a vast empire, made with skill and consistency, yet it left no trace in the documentary record. It suggests a category of knowledge that was purely practical, transmitted through demonstration rather than writing, and lost when the social structures that supported its use collapsed. The Roman Empire kept extensive records, yet somehow this particular piece of everyday life slipped through the cracks. Every dodecahedron found adds to the collection, but none has yet been discovered in a way that definitively reveals its purpose. And so they sit in museums, geometric and mysterious, reminders that even well-documented civilizations can keep secrets simply by failing to write something down. The Phaistos disc. In July 1908, Italian archaeologist Luigi Pernier was excavating the Minoan Palace complex at Phaistos on the southern coast of Crete when he uncovered a fired clay disc approximately 6 inches in diameter. Both sides were covered with stamped symbols arranged in a spiral pattern, running from the outer edge toward the center. 241 individual symbol impressions made using 45 distinct signs. The disc had been deliberately crafted, carefully inscribed, and then baked until hard. It was roughly 3,700 years old. Pernier recognized immediately that he was looking at something unusual. The symbols weren't scratched or painted, they were stamped into the soft clay before firing, using pre-made seals or punches. This meant someone had created a set of reusable printing tools, individual stamps for each symbol, and then used them to compose a text. It's a printing technique that wouldn't become widespread until Gutenberg's movable type 3,000 years later. The Faestus disk, as it came to be known, has never been deciphered. More than a century of linguistic analysis, pattern recognition, and comparative study has failed to crack the meaning of its symbols. It remains one of the most tantalizing puzzles in archaeology, a text we can see but not read, a message transmitted across millennia with no translation key. The disk was found in a small room within the palace complex, deposited with other objects in what appeared to be a deliberate cache rather than everyday storage. The archaeological layer suggested it dated to the late Minoan period, roughly 1700 BCE, during a time when Cretan civilization was at its height. The Minoans were seafaring traders, skilled architects, and producers of art that still captivates modern viewers. They had writing systems, linear A, and a pictographic script, but the symbols on the Faestus disk don't match either one. Each symbol is distinct and carefully formed. There are human figures in various poses, animals, including birds and fish, plants, tools, and geometric shapes. Some symbols appear frequently, others show up only once or twice. The spiral arrangement moves inward on both sides, divided by lines into what appear to be groups or words. The total number of signs per group varies, suggesting different lengths of semantic units. It has structure, it has organization, it looks like writing. But proving it's writing and then reading it are two very different challenges. For a script to be deciphered, you typically need one of several things: a bilingual text that provides translation, enough examples of the script that statistical patterns emerge, or recognizable names and places that anchor the language to known historical context. The Faestus disk offers none of these. It's a single example. No other disk, tablet, or inscription has been found using this particular set of symbols. It's linguistically isolated. Scholars have tried various approaches. Some attempt to link the symbols to known Minoan pictographs or linear A signs, looking for visual similarities that might indicate a relationship. The connections are tentative at best. The disk's symbols are more pictorial, more detailed than the abstracted signs of linear A. They could represent an earlier stage of writing development, a parallel system used for a different purpose, or something else entirely. Others have tried numerical and pattern analysis, looking at the frequency of symbols, the way they cluster in groups, and their positions relative to each other. Certain symbols appear to function as potential word dividers or punctuation. Some signs show up predominantly at the beginning or end of groups, suggesting grammatical roles. But without understanding the underlying language, statistical analysis can only go so far. You can identify patterns without knowing what they mean. There's also the question of what kind of text it is. Is it administrative, a record of goods, tribute, or transactions? Minoan palaces kept extensive records, and linear A tablets are largely inventories and accounts. Is it religious, a hymn, prayer, or ritual instruction? The careful craftsmanship and deliberate deposition might suggest something ceremonial. Is it literary, a story, poem, or historical account? The length seems right for a narrative text, longer than typical administrative records, but short enough to be contained on a single disk. Some researchers have proposed it's not Minoan at all, but an import from another culture. The unique symbol set could indicate a foreign language, something brought to Crete through trade or diplomatic contact. This would explain why it doesn't match local scripts and why we haven't found other examples. It might be a one-off document, carried from its place of origin and deposited in the palace for reasons we can only guess. Then there's the printing technology itself, which deserves attention separate from the text's meaning. Creating individual stamps for 45 different symbols suggests a system intended for repeated use. You don't make a set of printing tools for a single document. You make them because you plan to produce multiple texts. But if the Faestus disk was part of a broader printing tradition, where are the other examples? Were they made on perishable materials that didn't survive? Were they melted down or destroyed? Or is the disk genuinely singular, an experiment that didn't catch on, a technique developed and then abandoned? The stamping method itself shows sophistication. Each symbol was pressed into the clay with enough force to create clear, deep impressions, but not so much that the disk warped or the clay tore. The spiral layout required planning. You have to know how much text you have and how it will fit before you start stamping from the outside in. Errors would be difficult to correct. Once a symbol is stamped and the clay begins to dry, you can't easily remove it. The finished disc shows no obvious mistakes, no corrections or overwrites. Whoever made it knew what they were doing. Material analysis of the clay indicates it's local to Crete, so the disc was made on the island rather than imported fully formed. The firing temperature and technique match other Minoan pottery from the same period. It was created with familiar methods, even if the content is unfamiliar. Various amateur and professional attempts at decipherment have been published over the years. Some claim the text is Greek, others suggest Luvian or Lycian, and a few propose connections to languages even further afield. None have gained widespread acceptance, largely because the methodology is circular. Start with an assumption about the language, force the symbols to fit phonetic values from that language, and produce a translation that may or may not make sense. Without independent verification, these remain speculative exercises rather than proven readings. What stuns scientists about the Phaistos disc isn't just the mystery of its content, but what it reveals about the fragility of communication. Here's a text created with advanced technique, preserved through careful firing, survived thousands of years intact, and yet it remains silent because the context that would make it readable has vanished. The Minoans had at least 3 writing systems, possibly 4 if the disc represents a separate tradition. Most of those scripts remain undeciphered. Linear A, despite hundreds of examples, still resists translation because we don't know the underlying language. The disc sits behind glass in the Archaeological Museum of Heraklion, its spiral text visible to anyone who visits. You can see every symbol clearly. You can count the groups, trace the pattern, note the craftsmanship. And yet its meaning remains locked. A message from a civilization that could write, could print, could communicate across time, but couldn't ensure that future generations would understand what they were trying to say. It's a reminder that preservation and comprehension are separate problems. We can save the text without saving the key to reading it. And sometimes, the most carefully crafted messages are the ones that go unheard. The Lycurgus Cup. In the British Museum's collection sits a 4th century Roman glass cup that appears green when light shines on it from the front and glows red when light passes through it from behind. The effect is dramatic, immediate, and shouldn't be possible with the materials available to Roman glassmakers. This is the Lycurgus cup, and it represents a level of material manipulation that predates modern nanotechnology by 1,600 years. The cup itself is a work of art independent of its optical properties. It's a cage cup, a form of Roman glassware created through an incredibly difficult technique. A thick glass blank is cast, and then the outer layer is carefully cut and ground away until only a delicate network of figures and background remains, connected to an inner cup by small bridges of glass. The craftsmanship requires extraordinary patience and skill. One wrong cut destroys months of work. The Lycurgus cup depicts a scene from Greek mythology, King Lycurgus, who opposed the god Dionysus, being entangled and killed by vines. The figures are rendered in relief, detailed and dynamic, frozen in glass. But it's the color-changing property that makes the cup scientifically remarkable. This isn't a trick of glaze or paint. The effect comes from the glass itself, from particles suspended within the material at a scale invisible to the naked eye. The cup remained in private hands for centuries before being acquired by the British Museum in 1958. It wasn't until the 1990s that researchers examined it closely enough to understand what was causing the optical phenomenon. Using electron microscopy, they discovered that the glass contains nanoparticles of gold and silver, pieces of metal so small that roughly 50 of them lined up would equal the width of a human hair. These particles are dispersed throughout the glass matrix in concentrations of about 40 parts per million. At this scale, metal doesn't behave the way it does in bulk. When light hits nanoparticles of gold and silver, the electrons on the surface oscillate in response to the light's wavelength. This is called surface plasmon resonance, and it produces dramatic color effects depending on the size and shape of the particles and the light interacting with them. In the Lycurgus cup, particles roughly 70 nanometers in diameter create the dichroic effect: green in reflection because shorter wavelengths scatter, red in transmission because longer wavelengths pass through. The Romans didn't understand plasmon resonance or electron behavior. They didn't have electron microscopes or spectroscopy equipment. What they had was empirical knowledge, the understanding that adding certain materials to glass in certain ways produced these effects. The question is, how deliberate was the process? Some researchers believe the dichroic property was intentional, the result of skilled experimentation and refinement. Roman glassmakers were sophisticated chemists in practice, if not in theory. They produced glass in a wide array of colors by adding different metal compounds: cobalt for blue, manganese for purple, copper for various shades of green and turquoise. They understood, through trial and error, that different additives created different results. Creating nanoparticles requires specific conditions. The gold and silver had to be introduced into the molten glass, and the mixture had to be heated and cooled in ways that allowed the metal to form discrete particles rather than dissolving uniformly or precipitating out as larger chunks. The temperature control and timing have to be fairly precise. Get it wrong, and you'd end up with muddy, opaque glass or no color effect at all. The fact that the Lycurgus cup exists as a finished, polished object with consistent color properties throughout suggests the makers knew what they were doing. They weren't lucky once. They controlled the process well enough to produce a complete, functional cup. That implies repeated practice, refinement of technique, and passing of knowledge. Other examples of dichroic Roman glass exist, though they're rare. A few fragments and smaller vessels show similar properties, confirming this wasn't a unique accident. But the technology didn't become widespread. Most Roman glass doesn't exhibit these effects. Dichroic pieces appear to have been luxury items, expensive and difficult to produce, destined for wealthy patrons who could afford glassware that took months to create and required rare materials. The specific recipe for creating the effect seems to have been lost during the decline of the Roman Empire. The knowledge was probably held by a small number of specialized workshops, passed down through direct apprenticeship rather than written instruction. When those workshops closed, whether due to economic disruption, invasion, or simply the death of the craftsman, the technique vanished. Later medieval glassmakers produced beautiful work, but they couldn't replicate the dichroic effect. It had to be rediscovered in the modern era, using scientific understanding of light and materials that the Romans didn't possess in theoretical terms, but clearly understood in practice. Modern replications of dichroic glass require careful control of particle size and distribution. Add the metal colloidally in a solution that allows nanoscale distribution and heat the glass in ways that keep the particles suspended without aggregating. The Romans likely achieved this through a combination of specific fluxes, carefully controlled furnace temperatures, and possibly mechanical stirring or manipulation during the melting process. It worked, even if they couldn't have explained why in terms a modern physicist would recognize. The Lycurgus cup also raises questions about intentionality versus serendipity. Did Roman glassmakers set out to create a color-changing cup, or did they stumble onto the effect and then learn to reproduce it? Both scenarios are plausible. Many technologies begin as accidents that craftsmen then learn to control. The first purple glass might have been a failed batch of blue that turned out beautifully. The first dichroic glass might have been an unexpected result of trying something else entirely. What matters is that once the effect appeared, someone recognized its value and figured out how to make it happen again. The cup would have been stunning in use, particularly in Roman dining contexts. Imagine a feast where the cups on the table shift color as slaves move around lighting lamps, as diners lift glasses to their lips, as sunlight streams through windows at different angles. It would have appeared almost magical, a demonstration of wealth and access to specialized craft knowledge. The mythology depicted on the cup, Lycurgus being destroyed for his opposition to a god, would take on additional layers when the very material seemed to defy natural behavior. What stuns scientists about the Lycurgus cup is the realization that nanotechnology isn't new. The term is modern, the theoretical understanding is modern, but the practical manipulation of materials at nanoscale has precedence reaching back millennia. The Romans controlled matter in ways we're only beginning to fully understand and appreciate, not through scientific theory, but through accumulated practical knowledge and skilled experimentation. It's a humbling reminder that ancient doesn't mean primitive. The tools available might have been different, the explanatory frameworks might have been absent, but the capability was there. Human beings have been solving complex material problems for thousands of years, sometimes achieving results that challenge our assumptions about when certain types of knowledge became accessible. The cup sits in the museum, green and red by turns, a testament to skill that was forgotten and had to be rediscovered. The Iron Pillar of Delhi. In the courtyard of the Quwwat-ul-Islam Mosque in Delhi stands a pillar of iron, roughly 23 feet tall, weighing more than 6 tons. It was forged during the Gupta period, sometime around 400 CE, and despite 16 centuries of exposure to Delhi's monsoons, humidity, and seasonal temperature swings, it shows almost no rust. A thin coating of oxide has formed in some areas, but the pillar remains structurally sound, its Sanskrit inscription still legible, its iron core intact. For a metal that normally corrodes aggressively in humid environments, this is remarkable. The pillar isn't unique because it's old iron. We have older iron artifacts from various cultures. It's unique because of its size, its composition, and its resistance to corrosion, despite conditions that should have degraded it centuries ago. Most iron from antiquity survives either in very dry environments where oxidation proceeds slowly, or as heavily corroded fragments that barely resemble their original form. The Delhi pillar stands upright, functional, and relatively pristine. Metallurgists have been examining this pillar since the 19th century, trying to understand how Gupta period ironworkers created an object with such unusual properties. The answers lie in the details of the metal's composition and the techniques used to forge it. Chemical analysis reveals that the pillar contains very little carbon. It's essentially wrought iron, forged from bloomery iron that was repeatedly heated and hammered to remove impurities. But the key to its corrosion resistance appears to be phosphorus content. The iron contains between 0.15 and 0.25% phosphorus, significantly higher than typical ancient or modern iron. In most contexts, phosphorus is considered an impurity that makes iron brittle and difficult to work, but at the concentrations present in the Delhi pillar, it has a protective effect. When iron containing phosphorus corrodes, the phosphorus concentrates in the rust layer, forming a compound called misawite, a crystalline iron-phosphorus-oxygen mixture that creates a thin, stable coating on the metal's surface. This coating passivates the iron beneath, slowing further oxidation. It's not that the pillar doesn't rust, it's that the rust forms in a way that protects rather than destroys. The effect is enhanced by the pillar's mass and the way it was forged. Gupta ironworkers created large blooms of iron by heating ore with charcoal in furnaces, then hammering out the slag while the iron was still hot. To create something as large as the Delhi pillar required welding multiple blooms together, heating pieces of iron until they were nearly molten, and then hammering them into a single continuous mass. Ancient smiths wouldn't have understood the chemistry, but they would have recognized that iron from certain ores, worked in certain ways, produced better results. The pillar's surface area relative to its mass also matters. A thick column of iron corrodes more slowly than a thin sheet because the ratio of exposed surface to internal volume is lower. Environmental factors play a role too, though perhaps not in the way initially assumed. Delhi has periods of high humidity during monsoons, which should accelerate corrosion. But the climate also has long dry seasons, and the pillar is exposed to intense sunlight. The cycle of wet and dry may actually help the protective oxide layer develop and stabilize. When iron corrodes and then dries repeatedly, certain oxide formations become more adherent and protective than they would in constantly humid conditions. Still, none of these factors fully explains why the pillar has survived in such good condition. Similar iron objects from the same period, even those with comparable phosphorus content, show much more corrosion. The Delhi pillar seems to have benefited from a combination of factors: composition, forging technique, mass, and environment that individually wouldn't be sufficient, but together create exceptional durability. The pillar's history adds context. It originally stood elsewhere, probably in front of a Vishnu temple, before being moved to its current location in the 11th century when the mosque was constructed. The Sanskrit inscription dedicates it to Vishnu and mentions a king, likely Chandragupta II, one of the most powerful Gupta rulers. The pillar served both religious and political purposes, a demonstration of devotion and a symbol of royal power. Creating such an object required mobilizing significant resources: the iron ore, the charcoal for fuel, the skilled labor to operate the forges and wield the hammers, and the time to complete what would have been months of work. Gupta period India was a center of metallurgical innovation. Indian steel, particularly Wootz steel, was prized throughout the ancient world for its quality. Damascus swords, famous for their strength and edge retention, were made from Indian steel exported to the Middle East. The techniques for producing high-quality iron and steel were well developed, and the Delhi pillar represents one application of that expertise. But even within the context of advanced metallurgy, the pillar stands out. Other large iron objects from the same period didn't survive as well. Gupta smiths clearly knew how to forge large iron structures. We have records and archaeological evidence of other iron pillars and beams, but most have corroded significantly or fragmented. Something about the specific conditions under which the Delhi pillar was made, the particular source of ore used, or the exact forging protocols followed, resulted in unusually durable iron. Modern metallurgists can explain the pillar's corrosion resistance in chemical terms now, but replicating it isn't straightforward. You'd need iron ore with the right phosphorus content, forging conditions that produce the correct grain structure, and enough mass to benefit from the protective effects of scale. It's technically possible, but it requires intentionally recreating conditions that the Gupta smiths arrived at through empirical knowledge rather than chemical theory. The pillar has become something of a tourist attraction, and for many years there was a tradition that wrapping your arms around it while standing with your back to it would bring good luck. The practice left oils and moisture from countless hands on the metal surface, which, ironically, may have contributed to the formation of additional protective layers. In recent decades, the pillar has been fenced off to prevent further contact, but centuries of human interaction may have inadvertently helped preserve it. What stuns scientists about the Iron Pillar of Delhi is the intersection of skill, material, and circumstance that allowed it to endure. It's not magic, it's metallurgy, chemistry, and practical knowledge accumulated over generations. But the fact that ancient ironworkers could produce an object with such exceptional properties without the benefit of chemical analysis or material science demonstrates a level of craft mastery that challenges simplistic narratives about technological progress. The pillar hasn't survived because it was protected in a climate-controlled museum. It stood outside for 16 centuries, exposed to everything the environment could throw at it, and it endured because someone, a long time ago, knew how to forge iron exceptionally well. That knowledge was passed down through apprenticeship, refined through experience, and applied to create something that would outlast the empire that built it. It's still there, slightly tilted now due to settling of the foundation, its iron surface dark and smooth, its inscription still promising prosperity to those who honor the gods. A monument to skill, and a reminder that the ancients understood their materials in ways we're still learning to appreciate. The Piri Reis map. In 1929, scholars working in Istanbul's Topkapi Palace made a striking discovery. Two fragments of a world map drawn on gazelle skin, created in 1513 by Piri Reis, an Ottoman admiral and cartographer. Reis had compiled this map using approximately 20 older source charts, including documents captured from Spanish and Portuguese vessels. The map depicted the Atlantic Ocean, African and South American coastlines, and something far more puzzling, what appeared to be the northern coast of Antarctica. That detail would spark decades of debate. Piri Reis was a skilled navigator and military commander who had served under his uncle, the famous corsair Kemal Reis. Throughout his career, he participated in numerous Mediterranean naval campaigns and compiled his knowledge into the Kitab-i-Bariyeh, the Book of the Sea, a detailed navigation guide. The 1513 map represented an earlier work created when Ottoman naval power was at its height and European charts were readily available through captured vessels. The map itself demonstrates remarkable sophistication. The African coastline shows reasonable accuracy for its era. The eastern coast of South America, visited by European expeditions in the preceding decades, appears with identifiable geographic features. The map includes illustrations of indigenous peoples and animals, decorative compass roses, and explanatory notes in Turkish. But the southern portion presents a puzzle that has captivated researchers ever since. Below South America, where modern maps show the Drake Passage, the Piri-Reis map depicts what looks like a continuous coastline with mountains and geographic detail. To some observers, this resembles Antarctica, specifically Queen Maud Land and the Antarctic Peninsula, as they would appear without their ice coverage. This interpretation created an immediate problem. Antarctica wasn't officially cited until 1820 and wasn't confirmed as a continent until the 1840s. How could a 16th century map show a continent, let alone its subglacial coastline, centuries before its discovery? This impossibility has made the map a focal point for alternative historical theories. If Piri-Reis depicted Antarctica, particularly its ice-covered terrain, then either his source maps predated the Antarctic ice sheet, requiring a complete revision of geological timelines, or they were created by a civilization with advanced surveying technology. Either possibility would fundamentally challenge established historical understanding. Mainstream scholars offer different explanations. The most widely accepted interpretation is that the southern portion doesn't depict Antarctica at all, but rather shows a speculative or distorted continuation of the South American coastline. Early cartographers often engaged in conjectural geography, extending coastlines based on limited information and theoretical expectations rather than direct observation. In the early 15th century, European geographers believed in Terra Australis, a massive southern continent needed to balance northern hemisphere landmasses. This wasn't based on observation, but on classical theoretical geography. Maps from this period frequently show large southern continents bearing no resemblance to reality. Piri-Reis may have simply followed this convention, extending South America southward and adding speculative detail. Another factor is cartographic distortion. Early maps used various projection methods and combining information from multiple sources, some using Mediterranean conventions, others using Atlantic or Portuguese methods, inevitably introduced errors. The southern features might simply be coincidental resemblances created through this distortion process. Proponents of the Antarctica interpretation counter with specific geographic correspondences: river estuaries matching subglacial valleys, mountain ranges aligning with actual Antarctic topography revealed by modern radar, and proportions seemingly too accurate for mere speculation. They argue this level of detail suggests direct knowledge rather than guesswork. But evaluating these claims is complicated. The map is fragmentary, only about 1/3 survives. We don't know which of Piri-Reis's 20 source maps contributed which elements or how much he altered information during compilation. He left notes mentioning a map from a Spanish sailor who'd sailed with Columbus and various Portuguese and Arabic charts. None of these source maps survive, making it impossible to trace the origins of specific features. Modern cartographic analysis produces mixed results. Some portions align reasonably with actual geography, particularly well-explored areas. Other sections show significant distortions consistent with speculative cartography rather than direct mapping. Interestingly, other maps from the same period show similarly enigmatic features. The 1531 Aurentius Phineus map depicts a large southern continent with surprising detail, while the 1754 Boucher map shows Antarctica divided by a strait, matching subglacial topography not confirmed until the 20th century. What remains undisputed is that Piri-Reis created a remarkably sophisticated map, incorporating diverse information and serving practical navigation purposes. Ottoman cartography was advanced, and his work represents a synthesis of Mediterranean, Arabic, Spanish, and Portuguese cartographic traditions, reflecting how information circulated during the age of exploration. Yet perhaps the genuine mystery isn't what the map shows, but why this particular artifact has captured imagination so persistently. Maps claim authority, they represent reality. When a map shows something unexpected, it creates tension. Either the map is wrong, or our understanding of historical knowledge is incomplete. That tension creates space for speculation. The map hangs in the Topkapi Palace Museum, carefully preserved behind glass. Scholars can examine every line and notation, but the questions it raises, what Piri Reis knew, what his sources knew, what they intended to depict, remain difficult to answer definitively. Maps are interpretations, not mere recordings. They show what cartographers believed existed as much as what they directly observed. And so the Piri Reis map remains controversial, not because the physical artifact is mysterious, but because interpretation isn't settled. It's a reminder that even with the object in hand, even with the ability to study every detail, certainty can remain elusive when the context explaining intent has been lost to history. 6 artifacts, 6 reminders that human capability has always exceeded what the historical record preserves, and 6 invitations to keep looking, keep questioning, keep trying to understand the people who came before us. If you want more journeys to the ancient world, subscribe to the channel and turn on notifications so you never miss the next episode.